Hi everyone, thanks for joining us today. This event is brought to you by DataTalksClub, which is a community of people who love data. We have weekly events. This is one of such events. If you want to find out more about the events we have, there is a link in the description. Go to the description, check it out. It has quite a few events that we plan, so check it out. If you see something interesting, register, sign up. Then if you haven't subscribed to our YouTube channel for whatever reason, now it's the best time to fix it. There is this red button below the video. Click on this and you will get notified about all our future videos. And we have an amazing Slack community. If you join it, you can hang out with other data enthusiasts. So I do suggest to do this. You're missing out if you are not there. Last but not least, we have an amazing course starting soon in September. So this course covers the basics of machine learning engineering. There is also a link in the description. So if you're watching it right now and you want to learn more about machine learning engineering, check it out. It's totally free. Yeah, you'll like it. During today's presentation, you can ask any question you want, and I will be asking these questions. And by the way, how do you prefer? Should I ask you questions at the end, or should I interrupt you if there is a relevant question and ask you the question?
I'd prefer at the end, if that's okay.
Yeah, that is totally okay. So we will keep the questions at the end. So there will be a Q&A session, and there is a link, pinned link in the live chat that you can use for asking questions. I think that's all. You're probably here not for me talking about this stuff, but for the fun stuff. So now the floor is yours. Please start.
Great. Just before I start, I've actually got a fan on in the background because it's very warm here. I just want to make sure it's not interrupting the audio at all.
I cannot hear anything, but also I have a fan. That's why maybe I don't hear it.
Okay, cool. If anyone watching live can hear a fan in the background, let me know and I will turn it off. Great. So firstly, I'd like to thank both Alexei and Francis for inviting me to give this talk with DataTalksClub. It's my first time, hopefully not my last. And so today I'll be talking about feature engineering for time series forecasting. And so this talk, before I go on, let me just quickly introduce myself. So my name is Kishan, and I work as a data science manager for a luxury fashion e-commerce company called Farfetch, where I work on time series forecasting and pricing optimization. Before I entered data science, I did a PhD in physics, working on building models of abnormal heart rhythms and doing large-scale time series analysis on that. I also like to contribute to open source when possible. My most relevant recent contributions would be to stats models, where I contributed some additional functionality to the time series decomposition methods there. In collaboration with Soledad Gali, I'm also building an online course on the same topic, feature engineering for forecasting. If you're interested, please check it out. And you can find all the slides today already on GitHub in the link there.
Maybe you can send me the links and I will post them in the live chat and the description so people can check them out right now.
Oh, let me just open and send that.
At least link to the slides and then people will be able to copy the slides.
I've just sent the slides there in the chat.
Did you?
Great. Yes. Have you received it? In the live chat. You should have seen someone.
In the live chat. Okay.
Yeah.
Maybe you should send it in Zoom, because in the live chat,
okay.
YouTube might block links that are not coming from the stream owner.
Okay. 1 second. Let me just.
Sorry, everyone, but I think you might want these links now, because later you will have to come back and then find it. Okay, now I have the link and I will post it to live chat. Sorry for the interruption. Now you have the link.
Okay, perfect. Now onto the actual topic. So what is this talk about? This talk is all about how do we convert a time series forecasting task when we want to predict the future value of a sequence or a set of sequences, and convert that into a tabular machine learning regression task where we have a table of features and a target variable. And this allows us to use some of our favorite models like linear regression, random forest, and so on. And so there are two main themes to this talk. One is how do we do forecasting using traditional machine learning models? And then secondly, how do we build good features when we start doing that? And so we'll start talking about how we can do time series forecasting using machine learning models. So I just want to motivate why we'd want to use machine learning for forecasting by way of an example. So a couple of years ago, there was a Kaggle competition called the M5 forecasting competition, where the objective was to predict the sales of a set of goods from Walmart. And this was an interesting problem because of some characteristics of the data set. There was a very large number of correlated time series that we had to forecast. There was over 30,000 product store combinations and therefore over 30,000 time series to forecast. The products lied in a hierarchical structure. So a given product could belong to a particular department, which belonged to a category. The sales of a product belong to a store, which could belong to a state, and so on. So there's a hierarchical structure in the data. You can see examples of the time series here on the bottom right. And as you can see, they have a varying length. So each time series can come online, as it were, at different points in time. And just from looking at the time series, you can see that there's a high degree of sparsity and intermittency. There's no obvious seasonality or trend when looking at this data. Also, we would imagine that exogenous variables or features like the price, promotional activity would also be important in forecasting the sales of these products. And we would also expect multiple seasonal patterns. So you might expect a weekly pattern because the weekend would be different from weekdays. The summer will be different to the winter. And so we have multiple seasonalities. Now, what was interesting is for this type of data set, it turned out that all of the top performing methods that won the competition were actually quote unquote pure machine learning models. And they were better than all of the traditional statistical benchmarks used for time series forecasting, such as exponential smoothing, ARIMA, and so on. And so in a lot of the top the top winning solutions, we saw light GBM. And it turns out that machine learning models like light GBM were able to learn simultaneously across multiple different time series and integrate these exogenous features. And overall, that allowed it to give you a better forecasting accuracy. The other advantage of using machine learning is that it gives you access to other tools and options. For example, you could specify the sample weights, which would allow you, for example, to give more weight to recent data than data in the far past. You can also specify custom loss functions, and actually, in the winning solution, a custom loss function was actually used, and so you get all this for free just by using machine learning models here. That being said, you should not neglect our simple traditional statistical baselines. Over 90% of the participating teams did not beat a simple statistical baseline model, exponential smoothing. And that means we should still use these as benchmarks. And even the top 50 solutions only improved on exponential smoothing by between 15 to 20%, depending on the granularity of the time series we were looking at. And so as a result, we should still continue to benchmark against simple methods and not rule them out entirely. Now, overall, my advice is that we should use kind of simpler, more traditional methods when we're dealing with what I would kind of call easy time series. That is where you see a very strong seasonality or trend. You have a very small number of time series. They're not correlated with each other. So you could just learn one model per time series. You don't see a lot of sparsity or intermittency. There's very little exogenous features, in which case you're probably better off using something like ARIMA or exponential smoothing or Profit. But you should consider using machine learning models when you have a much more complex problem that you might encounter in a business setting such as this. And so that kind of hopefully gives you some motivation of when to use what kind of method. So how do we go about doing forecasting with machine learning? So we start off with our time series here. It's just a fake time series, which I'm going to call sales. And we have all of this information up to time t, and we want to predict the sales at time t plus 1. And so we want to convert this time series into a table of features and a target variable. So how do we create our target variable? In this case, we're just directly going to use our time series because that's what we want to predict. And when we create these feature vectors, we want to create features which only use information in the past. And so we're only using the data that's known at the time of the target. And this will allow us to avoid what is called look-ahead bias. This is where we use information from the future to predict the future, which would result in data leakage. And so I can show you what we would do here. So when we're constructing the feature vector for this target here, perhaps in the future, we're basically going to create some function from the previous values. And the simplest thing we can do is just to directly use those past values. And so we can create a feature vector here from the previous values of our time series. And so here we're using what's called a lag of 1, a lag of 2, and a lag of 3. So lag 1, lag 2, lag 3. And so we can populate our feature vectors and associate them with our target in this way, and it doesn't create any data leakage. And so we go on, and of course we're going to have some missing data at the start of the time series because we can't lag any further as we go back. And so here we've derived some features from the past value of our target time series, and these are called lag features. And you can also create more complex features from the previous values, and we'll get onto those later. Another class of features are those where you know the value both in the past and in the future. One example might be advertising spend. You might have observed the advertising spend in the past and you observe the sales, and then you might have a budget, and so you know what the advertising spend is in the future. And so that's quite easy to create a feature from. You just use it directly. You might also have features where you know the value in the past, but you don't know it in the future. Examples would be weather-related features. You might have observed rainfall in the past, and that might affect the sales of your product. Maybe you're selling ice cream, I don't know. And then in the future, how do you populate this feature? Well, there are a few things you can do. One is you have to use an alternative forecast. So you use a weather forecast and you pull that from somewhere else and you use that as your feature. Alternatively, you have to create your own naive forecast. So you might extrapolate from the previous value and project that outwards. And if neither of those work for you, then you might have to also use lag features for these type of features. So rather than projecting it out, you'd use the lag value of rainfall. So to predict the sales tomorrow, you'd look at the rainfall today, for example. Lastly, we have a set of features which probably isn't discussed as much, one which we'll call static features. They're called static features because they typically represent metadata about your time series, and they don't change for a given time series. So you might have the sales in a particular country like the UK. You might ask, why is this useful? It's useful when you start dealing with multiple time series, because then that metadata can vary between time series. So you might also have the sales in Germany or in other countries, and then you can try and have your model learn information about different groups of time series, and that's where static features come into play. And so now we have a group of features organized in a table, and we have a target variable. And so we can form our training data here. We'll come on to later around how we can process our categorical features and dealing with missing data and that kind of stuff. But essentially, we have our training data, which allows us to take whatever standard sklearn type model we have, run .fit, and then we can predict one step into the future. Now, in practice, we will want to do multi-step forecasting. We don't want to forecast just one step into the future. Typically, we forecast multiple steps into the future. And so there are two main methods that allow us to do this. One is called direct forecasting, and the other one is called recursive forecasting. In direct forecasting, we're going to directly predict the future values. Effectively, we're going to use the same features built from the past values, but we'll build models on different target variables, which means we'll have multiple models for each different target variable, but effectively the same features. And so you'll have many models per forecast time step. So let's just illustrate that. So let's say you're creating your feature vector and you start at this time point here. You create your feature vector of lagged values and you associate that with your target variable for one step ahead. Now you also want to build a model that predicts 2 steps ahead. So you use the target variable, which is 2 steps after the time frame you're considering here. And likewise, a third time step. So now we have the same feature vector, but multiple different target variables. And so we can then drag our time line forward here and construct our feature vectors and our target variables. We can then effectively pass the same feature vectors to these different models and give them different target variables during training. And so when we pass our input feature vector representing our most recent time horizon, when we pass that input vector to our models, you will then get a forecast for each model, giving you a different forecast into the future. So we'll have a model that gives you a 1-step forecast, another model that gives you a 2-step forecast, and so on. This has the obvious downside that you're now going to train multiple models per forecasting step. If you want to do 28 days into the future, you'll have 28 models, and that introduces a lot of complexity. So is there a simpler way of doing this? Well, this is what recursive forecasting tries to take into account. And so with recursive forecasting, you build your features and you fit the model once. And then you're going to recursively use this model. And I'll show you how. So you build your model and you predict your one step ahead forecast as normal. Now you're going to append that forecast back to your original training data. And now you recreate your features on the target variable with your forecast. And then you plug that back into the model to get you your next forecast and so on. And this way, you can use one fitted model to predict multiple steps into the future. Now, let me show you exactly how that works on our tabular data set. So let's assume that we've already processed our static features, our future unknown features, and our future known features. And so we're just dealing with our lag features here. And now we have to build these iteratively. So in the first step ahead, we're just going to build our features from the past values as we've shown. And then we predict one step into the future. And now we append that prediction back to our target variable. And now we recreate the feature vector from this augmented target variable here with our forecast. And now we can do .predict again on this feature vector, append the forecast, and continue. And in this way, we can do multi-step forecasting using just one model. So let's just talk about the pros and cons of these methods. So one of the advantages of direct forecasting is that each model you're building is directly optimized for each forecasting step. If you're going to build a 10-step ahead forecast, then you've built a model that does precisely that. And this is to contrast it with recursive forecasting, where you only built one model which optimized on building a one-step ahead forecast. And you might imagine that the way a model uses features to do a forecast in the near term might be different than in the long term. And so that's some of the advantages and disadvantages on that point. The cons of direct forecasting are obviously you're now having to use multiple models, which involves a computational cost. It's harder to maintain. And also these forecasts are all independent. The forecasting model to forecast one step ahead is independent from the second step ahead and third step ahead and so on. So you can't guarantee that they'll be correlated or near one another. So some of the advantages of recursive forecasting is that you only have one model, which means it's less computational time. And the forecasts, by definition, they are dependent because you're using the forecast to generate your next forecast. And so they're correlated. One of the disadvantages is that you now have a lot of additional code complexity to iteratively create your features, append them to target variable, and so on. And I'll show you how you can overcome that with some open source libraries later. Also, you'll have the propagation of errors. If your one step ahead forecast has a significant error, then that will obviously propagate to your second step ahead, your third step ahead, and so on. And so in that way, these errors propagate. And as we've mentioned, it's only optimized for one step ahead. And so these are some of the things to keep in mind when you're considering whether or not to use direct or recursive forecasting. Now I just want to talk a little bit about how we would validate our forecasting model. So traditionally, when we work with tabular data and we want to do some kind of cross-validation or a train test split, we could just randomly shuffle the data from our original data to a training and test set. And we could do that in a random manner because we can assume that each row is independent. And that way we can therefore randomly split the data. The problem now is when we're dealing with time series data, and despite the fact we're still working with tabular data, you cannot split randomly because the time ordering in your data means each row is no longer independent from one another. If you were to randomly shuffle this data set, you might have values in the future land in your training data, values from the past landing in your test data, and then you're using the future to predict the past. And so you will have a very inaccurate idea of how well your model actually performs in practice. So instead, you need to split by time to replicate the actual forecasting process. What does that look like? So in time series cross-validation, you'll arrange your data by time and you have your full data set. And then you'll split the data by certain time horizons, and then you'll train your model using data prior to that horizon, and you'll forecast to some horizon in the future, and then you move that window forward. And so in this way, you do get multiple folds that you're able to train your model and also test. And so you have to take the time ordering into account. That's how you do time series cross-validation. So just before we move on to feature engineering, I really want to highlight the differences in the machine learning workflow between doing your standard regression and classification tasks versus doing forecasting. Whilst we're still operating with tabular data in both cases, the workflow when it comes to writing your code will actually be very different. So for a start, when we want to do our train test split, we could do random allocation when we're doing our typical random regression and classification tasks. When we're doing forecasting, we need to split by time. When we're creating the feature and target variable, we could actually pre-compute our features and target variable before predict time, before we even touch the model when we're doing typical regression and classification tasks. Now, some of our features are actually built from the target variable on demand at predict time. There's lag features when we did recursive forecasting. And this means that you can't just pre-compute all of your features prior to predict time when you're doing recursive forecasting, for example. This also changes the way that the model behaves at predict time. So when you're doing regression and classification tasks, you only need the trained model, and then you could provide an input, and then you get a prediction. When we're doing forecasting, you need the trained model, but you also need the training set at predict time, because you need information from the training set to construct any feature that is built from the target variable. And so that means that you can't just have the trained model when you put your model into production. You also need to pass your training set as well. So it changes the way that you put models into production. And lastly, the feature engineering looks quite different. There are a lot of time series specific feature engineering issues, which can cause data leakage, where you have information flowing from the past, from the future into the past that you want to avoid. And I'll come on to that in the next section of this talk. So now I'm going to talk about feature engineering. So there's a lot of feature engineering when it comes to time series forecasting, and a lot of things just specific for time series. And so this covers a wide area, all the way from how do we impute missing data? How do we identify outliers? Can we transform the data, our time series, to make it more forecastable? For example, by applying certain transforms like the log transform, or deseasonalizing or detrending our data before passing it to our forecasting model. Can we encode, how do we encode categorical variables now we're dealing with time series? We can also extract a lot of information just from the temporal aspect of the problem. For example, from the calendar, like the day, the week, the month. Are there any particular holidays? We also extract a lot of features from past values of both the target and other features. And lastly, there's also a lot of information from the trend and seasonality in a time series. For example, are there change points? Is there a step change somewhere in your data? Is there some regularity that you can pick up from the seasonality and project that forward? So there's a whole host of methods to create features for time series forecasting, and are specific to time series. And we're going to cover some of the most important ones, and these were also used in the M5 forecasting competition. And so let's talk a bit about those. And so one thing you might be asking is, well, what data can I use to build features? And the answer is, well, any data that you know at the time of making a prediction, including any knowledge you have about future values of a feature, let's say, for example, your marketing spend. But you have to be very careful not to leak any data from the future into the past. And I'll show you how it's very easy for that to occur. It's easier to say than it is to do in practice. So I'll show you some points to be careful about. So let's look at a concrete example. Imagine that we have multiple products, and we want to, which means that we have multiple time series, and we have some global advertising spend, and we want to predict the future value of these products. Now, I'm going to represent that as a table here. So you have your time index, you have your product ID, and for each time series, we have a different product ID. We have our advertising spend, which is the same across both product IDs, and we have our target variable, which is just the sales. And so we want to predict future values of our products, and we might know the advertising spend going into the future, let's say. So the first question is how do we build our target variable for this example? So now we're actually dealing with multiple time series. And what you can do is if your time series are concatenated in this way, you can directly just use your sales value here as your target variable. One thing to note now is that the target variable actually contains sales values from multiple different time series, all within one target vector. And the model without features doesn't know that one observation belongs to the same time series, and it doesn't know that two different values belong to two different time series. You have to try and encode that kind of information in your features. So let's talk about the most simple feature that you can build, and it's one that I showed earlier, which are lag features. And this is where you're directly using the past values of the target variable or feature to predict the future values. The intuition here is that recent values of the target are likely to be predictive of future values. Likewise, another trick you can do here is something which are called seasonal lags. Let's say you know that your time series has weekly seasonality, then you can introduce this by just using a lag of 7 days, for example. So it's a very quick and dirty and very easy way of capturing weekly seasonality. And I'll show you in a concrete example where this works quite well later in the talk. So you could also use the lagged version of other target time series to predict other ones. So you could use previous values of one product to predict the future values of a different product. Now, the only disadvantage here is that if you have lots of products, you will end up creating lots of additional features. So really, this should only be considered where you have a small number of additional time series that you know to be correlated. And this is a very easy way to model the codependency between your various different target time series. And lastly, we might also want to use lagged values of our exogenous features. I'll give you a concrete example of that. One might be, for example, advertising spend. The advertising spend might have an impact on your sales today, but also tomorrow and the day after, and so on. The effect is distributed in time, and therefore you might want to use lagged versions of your advertising spend. So the advertising spend today, yesterday, the day before, and so on. And that's known as distributed lags because you're trying to capture this distributed effect in time. And so that's another use case for creating lag features from other features. And so what does this look like when you're building that on this kind of table? So when you're creating your lag features from your target variable, it looks very similar to what I showed before. You're just using the previous values, and likewise for your advertising spend. And so here we have the lag of 1 and lag of 2 for our advertising spend. And then you create your feature vector, you're associating it with your target value, and you continue in this way, and so on. And then you can build out your feature matrix like this. Now, it might be very tempting looking at this that you might just use pandas and then just shift your time series to create the lagged features. If your table does look like this, however, you just have to bear in mind that if you do just use shift, then you might accidentally introduce values from which belong to one time series, one product ID, and assign them to the wrong product ID at the edges. So ideally, you want to group by your product ID and then apply any transformation to an individual time series rather than operating on this table as a whole. So just to warn you, so that's one way that you might accidentally screw up your feature engineering there. Now, a question I had in the past was, you end up building lots of lag features if you do this. So how do you know which lag features to build? And so there are three main methods that we can do to try and narrow down which lag features we build. One is using domain knowledge. Another thing we can do is use feature selection and modeling techniques. And lastly, we could use what are called time series correlation methods. So let's give a specific example where domain knowledge can be quite helpful. So let's say we want to lag our target variable. What should we do? Well, the simple one is if you know the seasonality a priori, then that will help you build your seasonal lag. If you're working on a retail sales data set and you have monthly granularity, you know that you will have yearly seasonality. You have Christmas, you have Black Friday, you have events which repeat each year. And therefore, using a lag of 1 year would be an obviously predictive candidate to create. Another example might be electricity demand. Here we have an hourly electricity demand data set, and you'll have multiple seasonalities, daily, weekly, and yearly. And so in this case, you might build a lag feature which has a lag of 1 day, 1 week, and 1 year. So you can use any information you know about the seasonality ahead of time. And also you might have some intuition about how many recent lags to use. You might know that your time series is highly correlated to the sales over the past 1 or 2 days, but not, say, 20 days in the past. And so that kind of gives you some limit. And that can take you so far using some domain knowledge. But what if we want to use a more automatic method? Well, another approach is using feature selection and modeling techniques. So in this scenario, you just create a bunch of different lag features for both your target variable and any features which you think might be reasonable. For example, if you are using advertising spend, it's highly unlikely that the advertising spend from a year ago is going to predict your sales today. And so you probably don't want to create lag features up to a year ago, but maybe you choose several weeks and you create, say, I don't know, 14 or so lag features for advertising spend, and you do the same thing for other features and your sales. What you can do is then just use standard feature selection and modeling techniques like greedy feature forward selection. And those methods, those would be very time consuming. Other things you could do is use modeling techniques like lasso. So just build a lasso model to do a one step ahead forecast and let that automatically determine some of your most important features, which also optimize on forecasting one step ahead. So that's quite another easy way to try and narrow down on which features you want to use. And lastly, we have what are called these time series correlation methods. And the main idea here is you want to measure how correlated are these lag features with your target variable. And if a given lag feature is very correlated to your target variable, then it might be helpful. And so there are three main methods here. One is called the autocorrelation function, and another one is called the partial autocorrelation function. And what they do is they measure how correlated your time series is to a lagged version of itself at different lagged values. So here we have a retail sales data set where you have yearly seasonality. And on this graph here, we have what's called an autocorrelation plot. On the y-axis, we see the correlation of the original time series to a lagged version of that time series at different lags. And you see these little peaks, which occur at a lag of 12 and a lag of 24. And what that means is that the time series at a lag of 12 is much more highly correlated to your original time series than other lags. And so you can use these plots to try and identify, is a given lag potentially a good candidate to use for forecasting? And then we also have the cross correlation function, which allows you to measure how correlated the lag of different features are to your target time series. So not measuring the correlation with the time series to lagged versions of itself, but to lagged versions of other time series. And so you end up getting similar types of plots where you look at these and say, is the correlation high for a given lag? Okay, then maybe I might want to use that as a feature. So that can help you narrow down, make sure you don't build too many features. Let's move on to another type of feature, what we call window features. And this generalizes the idea of lag features, where rather than directly using past values, we're computing some function or summary statistic over a window of past data. So rather than directly using the past three lags, we're going to look at the mean of the past three values, for example, or the standard deviation, which gives us a measure of the volatility of our data, and use that to predict future values. This can be helpful because, for example, by taking the mean, you're also smoothing the data. So if there's a lot of volatility in your data, then that can also be helpful. So what does this look like in practice? So what you're going to do is you have a window of some size, and then you apply a set of summary statistics, for example, the mean and the standard deviation, and you roll that through your data to create your feature vectors. One thing to note here is that we're actually lagging our rolling statistic. We're not simply using pandas, taking the rolling operator and then applying dot mean. We're also doing a lag of 1, because if we were to not take the lag of 1, we would have then assigned the feature vector to this row over here. I don't know, can you see my mouse, by the way? Yeah, we would have assigned it over here, which means that you're then leaking information because you're using information at the time of prediction to create your features, and so you create leakage. So you also have to do some lagging here. Once again, another easy way that you might accidentally leak data from the future into the past. So one way of picking the window sizes is a technique called nested window features. And this is where you will look at window sizes on different orders of magnitude. So you might look at window sizes on the orders of days, weeks, and months. And in that way, you create a feature which captures some information at different time scales. And you let the model learn about some behaviors which occur in different time scales there. And so next, let's move on to static features. So as I described before, static features effectively represent metadata around your time series. So we might have something like the product ID. And so we have different time series here, which means that the static feature is different amongst these two different group of time series. And we might also have other types of static data. Let's say we have some other metadata about, say, the product category. Maybe one of these time series represents shorts, another time series represents watches. And then if you have a whole group of time series, you might realize that, say, the time series which are of type shorts have some kind of seasonality, but the watches time series don't. It'd be great if the model is able to learn these differences between these groups of time series. And likewise, to pass information that a time series, that the data in the target vector comes from the same time series. And so you can do this by finding ways of encoding these static features. So the most common way of dealing with these kind of categorical variables in tabular data sets is what's called target encoding. And this is where you group by your categorical variable, and you simply take the average of the target variable for each category over the training data set here. And so what we'll do here is we take, for skew1, we'll take the mean of our training data, and then we'll pass that value as our encoded value here, and we'll do the likewise for skew2. Now, this may look okay. However, there's a subtle data leakage going here. So whilst there is no leakage between the training set and the test set, because we only computed the encoding on the training set, the target is being leaked from the future values to the past values in the training set. And this can actually cause some degree of overfitting to this feature here. And I'm going to show you why. So if we plot our time series like this and see what it means to create the target encoding, it'll become more obvious. So imagine this is our time series. We've split it into our training data and our test data. If we take the target encoding by just taking the mean of our training data, like we do here, and let's say the mean is 14.4, and now we impute our target, our product ID by 14.4, well, that means that the model, when it's predicting values, let's say, at this value here, at this point in time, it has access to information in the future because the future values were used when computing the mean. And so now the model is able to determine that, oh, well, the time series is going to increase because there's an increasing trend. And so there is still leakage from future values to past values by taking the target encoding in this manner. So how do you overcome this? Well, one simple adjustment you can make is to ensure that you only use the values you know at that point in time. So when you create this this target encoding at this time point 2, you only use the values before time step 2 to create that encoding. And then at time step 3, you use all the values prior to that. So effectively what you have is this expanding window going across your data set, and you're taking the mean across that expanding window. And in this case now, there is no data leakage within this feature. Now you might have a question about how do we compute the encoding for future values? So if you're doing one step ahead forecasting, this is not a problem because we can still take the mean of the target to all at all points prior to that. And so that's what we can do there. If we're using recursive forecasting, then we need to recompute the encoding at predict time to ensure that the way that you've created your target, your encoding is consistent with how you've trained the model. So in this case, we would make a one step ahead forecast, you append that to your target vector, and then you recompute the encoding with your forecast in the data in this way. So you have to adjust the way that you compute your encoding. And likewise, you'd have to make an adjustment for direct forecasting as well. So the way that you compute your encoding depends on the method that the forecasting method that you use. So what are the key takeaways so far? Well, data leakage is a huge risk when creating features from the target variable and future unknown variables. And therefore, you should only use data that you're going to know at the time of that target variable. And this also means that handling features at predict time can vary depending on the forecasting method that we use. And this introduces a lot of code complexity when implementing this in practice, which is why it'd be helpful if there were some good open source libraries to help us with that, which is what we're going to talk about now. So what libraries are out there? So if you're interested in just doing feature engineering, that is just creating the features on some data set and not doing forecasting, then there's some cool libraries out there. TS-Fresh and Feature Engine are some. And TS-Fresh computes a whole host of various different time series statistics. So one time series goes in, multiple statistics come out. Now, if you're interested in that whole forecasting workflow and using tabular data and machine learning to do that, well, both Darts and SK-Time help you do that. So these packages have a much larger scope than just doing forecasting with machine learning, but they also offer these services, and that's really, really cool. So they implement these direct recursive forecasting strategies. They also contain transformers to help you build pipelines, and so on. And so the advantage that they bring is all of the complexity in, for example, creating lag features, dynamically recomputing your feature at predict time. It takes care of all of that for you under the hood so that you don't have to worry about that. And so that's one reason to use these open source libraries rather than implementing that logic yourself. Now, I just want to walk through a concrete example, which I've implemented in Darts. No reason for that. I would also highly recommend looking into SK-Time. Both of them are fantastic libraries to use. Now, how do we do this with Darts? So imagine this is our pandas series that we have. We have our index, we have our values, and what do we do? So from Darts, we have to use a wrapper around our pandas series or data frames. And so we have to import a class called a time series class, which is just a lightweight wrapper around a data frame. And then what does the heavy lifting is what's called this regression model class built into Darts. And that's the class that will do the construction of your lag features and all this kind of things under the hood. And then we can use whatever regression model we like. We could use random forest, linear regression, whatever we want from sklearn. You could also use gradient boosted trees from XGBoost and LightGBM and so on. So we import that here. So we start off by converting our pandas series here to a time series object. We might want to hold out the last 24 data points so that we can treat that as our test data. And here we specify and train the model. So we have our regression model, and here is where we specify the lag features. We're not creating the lag features separately and then passing them to the model. We're specifying them as part of the model definition. So here I'm saying lag the target by 1, 2, and 12. And here we're going to see where we have a yearly seasonality. A lag of 12 would be quite helpful. The data is monthly here, which is why it's a lag of 12. Here we're going to pass a linear regression model. As I said before, it could also be a random forest, whatever you want. And then we fit the model, and then we can predict 24 time steps into the future. And as mentioned previously, you now also have to pass the training set at the same time when you want to predict. And so this is the forecast here. And it's fairly reasonable here. This is the airline's passenger data set, which is just a linear regression built off features, which is the lag of 1, 2, and 12. So that's how you do recursive forecasting using linear regression on one time series and only lag features. What if you have external variables or other features? So let's say you've got advertising spend, or you might also want to use the month or year as a feature as an additional way of capturing seasonality. Well, you just create another time series object from your features. So here, let's say our features is the ad spend month and year. We filter our data frame and then create a time series object. And we store that in this variable called future cov, which stands for future covariates, which is the parlance that Darts uses. And then we just pass future covariates to our model.fit method. One detail I'll mention is that you could also lag your future covariates. So if you want to use the lag of the advertising spend, you can specify those lags as part of the model definition here as well. And over here, I'm choosing not to lag the advertising spend. Then we can just hit model.fit, model.predict. We pass our future covariates as well as our training data. And then we can also get a forecast out. So now we know how to do recursive forecasting using linear regression on a single time series with both lag features and exogenous features. Now let's deal with our last example here, which is where we have a much more complex example. We have multiple time series, and we have exogenous features, and we want to do lag features. So here we have our timestamp. A time series is defined by both country and product ID. So you have one time series per country product ID combination. Our target variable is here y, and we have our features. So Darts has a handy method called from group data frames, which will convert a pandas data frame, which looks like this, into a set of time series objects. So you specify the columns which define your time series, the time index, and the target variable, and it returns a list of time series. And that's how Darts handles multiple time series. It needs to take a list of time series. And we do the same thing for our features. So we have a list of features, and there's a one-to-one correspondence here. So this time series here corresponds to the features associated with that in this list here. And then we can simply pass all of our future covariates now in our model.fit method. And if we want to just, for example, predict a subset of our time series, then we can do that. So here we're going to say only predict the first two time series that we passed in our training set. And therefore, you're only going to need the future covariates for these first two time series. And now we have one model which was trained across multiple time series simultaneously. And then at predict time, it was able to produce multiple forecasts for each time series, which is pretty cool. Also, these time series, they didn't need to be aligned. The time series could have been defined at different time points. So here you can see this time series didn't even exist during this period of time. And so these indexes don't need to be defined. And so this is some of the advantages, once again, of using a tabular machine learning based approach. So I'm just going to conclude now so that we can answer some questions. So forecasting can be treated as a tabular machine learning task, and it can be competitive with our traditional forecasting models. The feature engineering and machine learning workflow is very different for time series forecasting, even though we're still working with tabular data. Forecasting comes with its own set of feature engineering methods and concerns around data leakage. And more support is increasingly becoming available for time series related tasks in the Python ecosystem. So I would continue to watch that space. And if you'd like to learn more about this topic, then do check out this course that I've created with Solid Gali. It's going to be launched in October, Feature Engineering for Forecasting. These are some of the references for some of the materials used to create this talk. And I'll now stop for any questions.
Yeah, you're probably tired of talking, right?
100%.
Yeah, I do have a question. So yeah, you need a small break, right?
Yeah.
So if you can you go please to slide 24? So in this slide 24, you were talking about.
It's going to take us a while to get back there.
Yeah, it will. So you were talking about like using predictions for some features. You call them I don't remember. This is a very complex word. Exogenous features, exactly, yeah.
Yeah.
So I remember this from my econometrics class, but in machine learning, we just call them features, right?
Yeah.
Yeah, you're still coming back.
It's going to take it. Sorry, 1 second.
Yeah.
Okay, I'm probably going to go over, and I've pressed back too many times, and my computer is now lagging. Sorry. There we go.
Okay.
Okay, cool. Can you still see my screen?
Yes.
Okay, perfect. Let's go to slide 24. Okay.
Yeah, 24. Okay, this rainfall feature, right? Mm-hmm. So here you use a feature and then you don't know the value, and then what you do is you predict the next value, right? Using some forecasting tool. So what I have troubles understanding here, or I have not troubles understanding, but like trying to figure out if it's okay or not. So what happens here is that during train time, we use the actual value, but then during the predict time, we use a prediction, right? Wouldn't it be better to use the prediction, also the forecast during the train time?
Yeah, so that you're absolutely correct. And this becomes a very tricky topic, because then the question is, do you want to use lagged versions because that's what you're using at predict time? You can do that, but it depends as well if you're trying to capture some degree of causality as well, because then you know the advertising spend on the day or the rainfall on the day had an impact on the sales. So if you're quite confident about what that value is in the future, then it should be okay. If you're lacking a lot of confidence, so other areas I see this is, for example, using page views, right? You might have page views of some product and you want to predict the future values, but of course you don't know what the page views are going to be in like 4 weeks' time, in which case you're better off using the lag values because you don't want to build a whole other model to predict page views. On the other hand, if it's something like weather, you might have more confidence about what that might be in the future. And therefore, in that scenario, it might be better off. Also, it depends if you want to do scenario forecasting here as well, that you're trying to answer the question, I want to know what my sales are going to be tomorrow if it's raining versus if it's not raining, if it's sunny or cloudy. And so you might actually plug in different values to try and assess different scenarios as well. In that case, you would also want to use the feature as it was on the day rather than necessarily lagging it.
Mm-hmm. And yeah, coming back to this weather forecasting, right? So I remember I was trying to think how to solve this problem, and then it's very easy to find the actual weather on that day on the internet, but it's very difficult to find the prediction, the forecast that was for this day, let's say one day before. Mm-hmm. And then like if you want to use to use the prediction for training your model, then how do you get data? Yeah, this is a very tricky topic. Okay, so maybe what I'll do now is I will share my screen. We have a lot of questions, and it's probably easier for you if I just share my screen, and then you can see them too. Okay, and by the way, sorry for the spam attack. While during the stream, I was Googling like how to stop it. So now there is a slow mode in comments. So now it's easier to handle spam. Anyways, so the first question is, do you have any resources to learn time series forecasting, both traditional and deep learning algorithms? So one resource obviously is the course you just mentioned. So there is another question like, how do I find the course? So there is the link in the description. I put the link. It's the first link there. Click on this and there will be a link to the course. But do you have other resources that you could recommend?
Absolutely, yeah. I mean, there's also a fantastic review paper which came out relatively recently over the past few months, which basically covers forecasting using machine learning and forecasting more generally, not just machine learning, so also traditional statistical models. It's a very chunky review paper, several hundred pages long. But if you're looking at just deep diving into specific areas of forecasting, I can link that review paper. I think the review paper is also actually in the references section of this talk. If not, I will add some references. I don't know, is it possible for me to post additional links back to the YouTube channel once we finish streaming?
Yeah, or you can we have the link to this thing, right? Yeah. So this is just to show people how to find it. So this is the first link here. And then you can just update your repo and put like all the links here.
No, sure, yeah, definitely. So what I can do is I can update the repo there to try and provide some more of those resources. On deep learning for time series forecasting specifically, I've not seen great introductory material. Typically, you need to have had some like prior knowledge of deep learning rather than it taking you from the very beginnings, and therefore, once again, it's kind of more paper oriented. There are some links which I found useful tutorial wise. For example, Google recently released a time series forecasting method called temporal fusion transformers. I think not like sometime over the past year or so. That was quite interesting, and they've got quite a nice little tutorial explaining that. So that can also help a little bit with the deep learning stuff. As always, if you're just getting into forecasting to begin with, I'd recommend Rob Heineman's book, Forecasting and I forgot the full name of the book. It's probably what I consider kind of the Bible entry textbook for forecasting.
Rob,
there we go. Forecasting Principles of Practice. Yeah.
Yeah, and then it's free. It's online.
Yes,
it's
exactly.
An R, but like R actually has a very nice ecosystem of like all these tools of libraries long before Python had anything similar. I think it's still like a few steps ahead of Python.
I definitely agree, which is why I had to make some contributions to stats models, because there'd be new stuff coming out in R which didn't exist in stats models, so you have to implement them yourself if you want them in Python.
Exactly. Okay, thanks. If you forecast once a month, should you retrain every month before you run your forecast?
It's a good question. It depends how much you expect the distribution of the data to change month on month. If it's only monthly, I would still encourage it, just because you can then refresh the model so it picks up any recent changes in your training distribution. I don't think it's computationally going to be too demanding to do that. The only downside is that you should at least check for model stability. Do your model coefficients jump around significantly every month? Are you ending up with very different models? If so, you want to examine why and which features are moving around. because you don't want to end up using a very different forecasting model effectively every month by retraining. And so that's just a way of just kind of sense checking whilst your machine learning model is in production.
Okay. Yeah, and if you run it every day, then maybe it's too cumbersome to retrain it, right? And
Oh,
then maybe you can retrain it like every month.
absolutely. And also, if you're forecasting, let's say 1 month ahead, your data may not have changed significantly. Like, I'm not sure having an additional forecast is actually going to be beneficial.
Mm-hmm. Okay, and that's actually a question from me. So while you were talking about, I think it was midway through your talk, and then even during the half of the talk, you said so many times that you should be careful. You can introduce data leaks, like you can accidentally use the data from the future. And my question was like how to guard against that. And I guess you partly answered that. You can use a library that,
I
can
guess,
do this.
yeah. I mean, I guess from a practical perspective, there are some libraries which will kind of handle. So, okay, when does that data leakage appear? When you create new features, it's typically when you're doing some kind of lagging or rolling window and using the past values, right? And so there are methods both in, for example, feature engine, skTime, darts, where this kind of behavior is covered for you in the transformers that are provided or in the model objects. So that will hopefully help guard you against that to some extent. In other cases, also for cross-validation, the other example I was going to mention as well is when you're doing cross-validation, you have to rebuild your training set as you're moving your time step forward during cross-validation, right? So that's another area where it can come into play. But once again, these libraries also help you with cross-validation. So I guess I'd say the easiest way is to use other libraries. If not, and you're going to build your own package, my other advice is use a lot of unit testing when you're building these. So build unit tests for any transformations you're building where you're going to create some kind of feature that uses like values and then lagging them. I think there was another comment as well I had. Sorry, I've not had enough coffee today. If it comes back to me, I'll come back to this topic.
Okay. So in the meantime, I think you will like this question.
Oh, yes.
Or
Okay.
I think
okay. It came back to me. It's come back.
Yeah, sorry, please.
So the other one is if you notice that your model is unreasonably good, if you notice that your forecasts are just very accurate, chances are you haven't suddenly built a crystal ball. You've somehow leaked data from the future into the past. And that's one reason why your forecast looks very, very good. And that's another sign that you might have actually leaked data from the future into the past. So that's another sanity check. Don't expect your forecasting models to look very good.
Yeah, thanks. I accidentally marked one interesting question as answered. So I clicked on this. So this question was, how would you deal with effects of events like COVID or financial crisis where behavior of the time series going forward might be very difficult?
I think this is such an interesting question, and I think something that everybody's facing in machine learning, where you're having to train on past data, where the distribution of the data has changed significantly. So, what can you do? Some simple things you could try and do. So, I mean, with time series forecasting, you would hope that the most important data is your recent data. And so, one thing you can do is potentially truncate your training data to only train over those time periods. Now you come into a more complex situation. You had COVID. COVID is kind of the behaviors of COVID probably are not as prominent now as it was during that period. So would you be under forecasting if, for example, COVID was still having an impact? And this is just very challenging to handle. Some things you can do is build two forecasting models, one with COVID data, one without, and then kind of take an average between the two. You have to just be very pragmatic and caveat the outputs that you provide to your stakeholders. Other ways you can handle this is potentially by introducing a new feature, or just giving more weight to recent time series, to recent data. So I mentioned earlier, you could use the sample weights option. So one thing you can do is just give more weight to recent time periods. Also, I wouldn't be averse to adding additional business logic on top of your machine learning output. Like, review the forecast. Does it make sense? Has the business been growing this fast in the past? Are you sure that if your forecast says it's going to grow 200% and it's only ever grown 30% year on year, maybe your forecast isn't so realistic and you might need to artificially constrain your forecast somehow, right? So yeah, this is the most practical advice I can give on that question.
Yeah, this one I think you answered. The course will be available in October. Am I right?
Yeah. So in October, we're hoping to pre-launch with most of the material we have up until then, which will hopefully be over 12 hours of material. It's quite a wide scope, and we want to continue adding to the course. So even after those 12 hours of materials, we'll still be adding more. So we'll have a pre-launch in October, which takes you quite a long way. But even after that, we're going to continue adding materials on a monthly basis.
But you can already subscribe to this and then be notified when it goes live, right?
Yes, exactly.
That's why you have this email box.
Yeah, exactly. So since it's live, you can get access.
So a question from Guido. I have a problem like your example, predict multiple series, and I need to predict only one step, but I have a lead time of 30 days. How would you fit predict? And lead time, like maybe I'm not sure what lead time is. Maybe you can answer that too.
I'm trying to interpret the question so I can properly answer it. So a lead time of 30 days, I'm assuming that means you're trying to predict 30 days into the future?
Or maybe it's a delay?
If it's a delay, I mean, the only advice, if it's a delay, then you should, I mean, the easiest things you do then is you have to lag your features, right? So, you know, the basic premise is with the information you have at predict time, if you need to predict, let's say t equals 31 and beyond, but you don't care about time t equals 0 to 30, then you will have to lag a lot of your features and use a lag feature. Let's say you're predicting whatever you have now up until 30 days and beyond. I've seen this in practice as well. So let's say you're doing recursive forecasting, and let's say you're interested in predicting time t equals 30 to 60, so 1 month into the future. You could still use recursive forecasting from time t equal 1 to 60, discard the first 30 predictions, and then just use the remaining 30, or just use direct forecasting where you directly build the target as being day 31 into the future. As long as you're keeping to that principle that you're only using the information that you're going to have at time equals 0, and then you're not using information between 0 and 30, you'll ensure that you avoid leakage.
Yeah, I'm afraid we're running out of time, but we have quite a few questions. So maybe what I can propose, I don't know if you can do this, but maybe we can move these questions to Slack and then take them offline. Would it work for you?
Yeah, more than happy to do so.
Okay, so I will, in a couple of hours, I will put all these questions to Slack. We have a special channel, I think it's called Events Q&A, something like this. And I will make an announcement in our announcements channel, so you will be able to see it. And I'll put the questions there and we can take them offline.
Great.
Okay. Yeah, amazing presentation packed with a lot of knowledge. I'm sure many people will rewatch it and use it, and I will certainly do. Yeah, thanks a lot. Thanks for joining us today. Thanks for sharing all this knowledge. And thanks everyone for joining us today as well, for asking questions, for being active. I apologize that we couldn't cover all your questions, but we will try to answer them anyways.
Yeah. Great. Thank you.
Yeah. So yeah, see you soon.